Howdy, this is your friendly neighborhood physics teacher here, and we're going to do Unit 7 on the College Board FRQs. So again, there's two questions. The first one is, states that this question is a long free response question. Show your work for each part of the question. And again, we have a lovely diagram that we get to draw. So we have something going on here. We have that. With that. So that's a theta. We have a hook with a line, a hook with a line, a hook with a line. That says A, B, C. This is labeled as pivot. And then this is labeled as, mass equals ms, and length equals ls. So there we go. That's what it looks like. Just imagine it being straighter because it's kind of wobbly on my side. And this part, oh geez, is definitely, this side was definitely longer than the other one. So there we go. So it says, in their physics classroom, students want to hang a heavy sign of mass ms and length ls, as shown in the figure above. The sign makes an angle theta with the wall. Without any support, the sign would rotate clockwise while its pivot would remain connected to the wall. The students can connect one support cable vertically from one of the hooks above the angle, as indicated by the dotted lines in the diagram. There's straight lines. Rank the three hooks located according to the amount of tension the support cable would experience if the students decide to support the sign from their location. Use 1 for the least tension and 3 for the greatest tension. If two locations would have the same tension, give them the same ranking. And it says location A, B, and C, and you're supposed to explain. This is another one of those ranking ones that if you just rank them, you're not going to get full credit. You have to explain. Okay. So to think about which ones would have a stronger tension. Same thing, you can think about a door. Why is the handle of the door farther away from the hinge than closer to the hinge? It's because it takes less force. So therefore, this one would be further away, would have less tension. So for the kind of an example expression would be, in order for the sign to hang successfully, the sum of the torques, remember torque is just rotating force, on the sign would have to equal 0. So they have to be at equilibrium. Since the necessary torque from the cable needs to be constant, equal in magnitude to the torque of the sign from the force of gravity, the way to get the smallest force is to use position C, which provides the biggest distance from the pivot. And then the equation you're using is your torque equals your distance, or your radius, so basically the distance from the pivot point times your force. And since there is an angle involved, you gotta use sine theta. So when you rank, so again, you didn't get any points for ranking at all. There was, in the explanation, there was no points for ranking. But if you were going to rank them, C would have the less force, then B, then A. And the reason is because the further you are from your pivot point, the less force you need. So part B, the students hang the sign with a cable, but the cable breaks and the sign rotates clockwise. The diagram below shows the sign at 3 different times as it rotates. So kind of the diagram shows you have your pivot point, and you have it here, kind of have it down here, and then we have it down here. It says that's time 1, time 2, time 3. Indicate at which time, if any, the angular acceleration alpha of the sign is greatest, or whether it is the same at all 3 times. So you're supposed to choose one. So again, kind of your explanation. Once the cable breaks, the only torque on the sign is the torque from gravity. So the only thing that's making it move is force of gravity. This torque is responsible for the acceleration of the sign, although the force of gravity at the point of application of the force, which is the center of mass, remains constant. The angle between these two vectors decrease, causing the net force, and hence the angular acceleration, to decrease as the angle decreases. So you kind of left your little saying, so as it will decrease. So basically you get a point for saying that angular acceleration depends on the net torque, and you also got a point for claiming that the net torque exerted on the sign decreases as the angle decreases. So again, if you're going to sit there and, because it asks you to rank them again, indicate which time angular is the greatest. Okay, so it'd be the greatest, it'd be at 1. So 1 would be the greatest. So the second part states, show that alpha can be modeled with, and it gives you a 3g sine theta over 2ls, the rotational inertia of the sign, and then it gives you your is is 1/2 ms/ls2. And so show that alpha can be modeled with. Basically what that is saying is you're trying to prove that alpha equals that. So you're trying to basically is saying, prove this. This is your answer. Try to get the answer to that. Well, you're dealing with torque, so you know the sum of the torques equals your molar inertia and alpha. Your torques so basically if you do your net torque just like anything else, so the torque that's going to be affecting it is force of gravity. So you have your force of gravity, but your force of gravity is linear. So that's when you have to basically put in here. Let's show. Okay. So force of gravity is but force of gravity is linear. If you remember, torque is your force times your radius, right? Well, in this case, we know the length, but we don't know the radius. So our radius would just be our ls divided by 2, because that's half that. So if we plug that in, we're being technical, so that'd be our force of gravity times ls over t. We do have a theta involved, so we're going to plug in our sine theta. So all of that gets plugged in on this side. So FG LS over 2 sine theta equals our IS alpha. We know what our I is, so we can plug that in. So we get our FG LS over 2 sine theta equals 1/2 MS LS 2 alpha. Our force of gravity is just our mass times our gravity, so we're going to put mass times gravity. LS2 sine theta equals 1/2 MSLS2 alpha. Now we're just trying to get alpha by itself. Did I put 2 instead of... Hold on. I realized it's a third, not a half. Did I write a third? I did. So it should be a third, not a half. Did I write a half up here or did I write a third up here? I wrote a half up here. That's what threw me off. So it's a third, not a half. It's like something's not going to add up here. That makes a little bit more sense. As I'm like, something's going on here. So now we have an L over here. We have an L over here. So we can cancel that out. We have an, and that's supposed to be MS. We have an MS over here. We have an MS over here. So our masses can cancel. So we're left with G, or 1/2 G sine theta equals 1/3 LS alpha. Bring the 1/3 over, multiply both sides by 3. So we get 3G sine theta over 2 L alpha. We divide both sides by LS. So we get that our alpha is 3G sine theta over 2 LS. There you go. So again, they've given you the answer. They're just wanting you to prove how you go from here to here. So you have to show all your steps. There you go. So that was part BI. So part C, B double I. So part C, the student wants to describe an angular velocity omega for the sign as it rotates. And they propose the following equation. So again, something they're giving us an equation for. It says that omega equals 3G sine theta over 2LST. Regardless of whether or not this equation is correct, does this equation make physical sense? So again, it's one of those situations that you need to try to get, how does this come across? So this equation does not make physical sense since the rod will swing down and then back up. Omega will get bigger, but then at some point will begin to get smaller. If the given equation were correct, the maximum value of omega would increase. So you got 1 point for indicating that the omega should get bigger, but at some time, some point in time, it should get smaller. And then you earned a point for providing an indication that provide the equation to be maximum value omega will increase. And the reason is because once, so as it's rotating, as it's going in a circle, your omega is going to get bigger, and then eventually get to the top, it's going to get smaller again. And so we have to show that. This, just because time, for one, it stated that this was your acceleration. So if this is your acceleration, you can just multiply it by t to get your velocity, which I guess in theory kind of makes sense, because if you think about your just basic, so meters per second squared, and you're timesing it, that does cancel, so that's what they're trying to say. But the trick is that's linear, this is rotational, we have a theta to deal with. So we have to think of the equation, so the equation doesn't make sense, because just as time increases, the whole entire system's going to keep getting bigger and bigger and bigger. And since we're going in a circle, eventually your theta would have to go back to 0 and then keep going. And so that this doesn't allow the theta to go back to 0 as time increases. So that's why it doesn't make sense. For D, student attaches a rotary motor sensor to the sign, recording omega and theta, and creates a graph of the magnitude of omega versus theta shown. And we have this lovely graph. So rads per second, and theta goes 6, 0, and this all goes all the way to 100. And we have something that goes something like this. So it starts out in between 5 and 6, and it ends somewhere between 80 and 100. That's a nice little curve aspect. It says 4 students independently derive equations and propose them to describe the motion of the sign. Which equation best describes the data collected? And it gives you, so our different equations are omega theta equals the square root of 3g cosine theta over ls, or it gives you the square root of 3ls cosine theta over g, or it gives you the square root of 3g sine theta over ls, or it gives you the square root of 3ls sine theta over g. You're supposed to justify your answer, what makes sense with the graph. So your correct answer is the first one. So your correct answer is the first one. And the little explanation they give is an equation, equation equal to omega must have units of radians per second. Of the choices of equations, only the 2 choices that have g over ls would give the correct units. Also, the graph starts at 0 velocity when the sign is first released, and as the angle approaches 0, the angular velocity approaches its max value. This is represented accurately by the cosine function. So basically, if you think about a cosine function is this, a sine function looks like that. So sine functions start at 0, cosine functions start up there. So that's how you could mark out the sine functions right away. But then you would sit there and look at your unit-wise, and you needed radians per second. And since your g is meters per second squared, and divided by your length, you were able to convert and actually get radians per second. There you go. That was part D. That's it. Cool. So that's question 1. Let's go to question 2. Questions 2. You have a table. Has a ramp. The height of the ramp is h naught. There's some type of wheel. And the height of the table is capital H naught. So there we go. It's kind of our figure 1. And this states that it's a short free response questions. Show all your work. So the ramp of height little h naught is placed on top of a table that has an edge that is a distance of capital H naught above the ground. A student places a hoop of rotational inertia of IH, mass m naught, and radius r naught at the top of the ramp, as shown in figure 1. The hoop is released from rest, so it's 0, and is allowed to freely roll down the ramp. Question A. The figure below represents the hoop at its traveling along the ramp. Draw a force diagram that shows and labels the forces, not components, exerted on the hoop. To clearly indicate at which point on the hoop each force exerted, draw each force as a distinct arrow starting on and pointing away from the point at which the force is exerted. Note, draw the relative lengths of all arrows to reflect the relative magnitudes of the forces. So they give you, in this case, they give you a grid, so the magnitudes do matter in this case. Magnitudes do matter. So they kind of give you a setup like this, and then they have your there. And it does say draw the forces from when it happens. So hopefully, the first force you draw is force of gravity. That always comes off the center. And then you have force of normal. That comes off the ground. And it's always perpendicular to the ground. And you have your force of friction. It's going to be hard, but you do want your force of gravity to be more than your force of friction. Your force of normal, I think that's, there you go. So probably make with the grid, make your force of normal the full 3 things. Maybe do your force of gravity. I know it's going at an angle, but maybe do 1, maybe do 4 just to make it. Then your force of friction, do like 1 or even a half of 1. And there you go. That's your free body diagram. And you leave that alone. If you ever need to put the components, like break down force of gravity into its x and y components, you draw it somewhere else. You leave that alone. So that's part A. Then it says, after it is released from rest, the hoop rolls down the ramp, launches horizontally off the edge of the table, and lands a horizontal distance d from the edge of the table. So now we're adding to the diagram and saying that from here to here is d. The situation is repeated, but the hoop is replaced with a solid disk of moment inertia, and it's stating that the disk has a less moment of inertia than the hoop, but mass is still mass naught, and your radius is still radius naught. So for B, in a clear, cohesive paragraph length response that may also contain figures and or equations, predict which object, the hoop or the solid disk, if either, will travel the greatest horizontal distance after each object is released from rest. So this one's also released from rest. rolls down the ramp and launches horizontally off the edge of the table. In your response, discuss the physical aspects of the hoop and disc that are similar and different, and how those differences affect the horizontal distance traveled. So there were 5 possible points in this. Kind of an example of the paragraph was the hoop and the disc have the same mass and are released from rest at the same height above the ground. Therefore, the hoop and the disc have the same initial mechanical energy. After they are released from rest, the hoop and the disc will have the same kinetic energy at the bottom of the ramp. However, the disc has a greater rotational inertia than the hoop. This means that the disc will acquire more rotational kinetic energy than the hoop. So basically, we're kind of comparing, so if we're going to do disc versus hoop. So they both start out with, and we'll do pink for same. So they both start out with the same gravitational. Same height, same gravitational, okay? Now, as they're rolling, so if we're going to, I'm going to make this more of an equation. So same gravitational. As it rolls, they're going to end up getting the same kinetic energy. But, so that this is your linear kinetic energy. But they're going to have different rotational kinetic energy. They're going to have different rotational kinetic energy. The reason is because of its moment of inertia. The moment of inertia for a hoop is bigger than the disc. So your hoop is going to have a bigger some of that energy, more of that energy is going to go into rotating it, because the disc is evenly transferred. So some of the mass is at the center of mass, it's evenly transferred. The hoop, all the mass is away from the center of mass. So it takes more energy to make it rotate than it would the disc. So however, the disc has a greater rotational inertia than the hoop. The disc has a greater rotational inertia than the hoop. That's not what you originally told me. There is a disconnect in their answer key and their explanation. Unless I read the explanation wrong, which it's completely possible. Let me go back and look. It says, after it's released from rest, the hoop rolls down the ramp. Then we put the disc on there. And it says, the solid disc of moment of inertia, our IH, is greater than our ID. Our IH is greater than our ID. Yeah, the disc because it has a greater moment of inertia than the hoop, or that the hoop will have a greater transitional. Okay, so there's a disconnect between the answers and the answer key. It's saying that the moment of inertia for the disc is greater than the hoop, but that's not what they told us. They told us that the moment of inertia of the hoop was greater than the disc. So I'm going to, I don't have the moment of inertia equations memorized on the top of my head, so I'm going to Google, give me a second. So moment inertia formulas, disk, solid, you're right, solid, disk versus hoop. Let's see, I'm going to compare. So yeah, so it says for your solid disk, so or your hoop or ring, this is for a hoop, your I is mr squared. For a solid disk, it's your I is 1/2 mr squared. So your disk is less than your hoop. So they had this part right, but when they did their explanation, they flipped their explanation. So my explanation was correct. Yay. Okay. So your hoop, sorry, I was looking at the key that AP Classroom gave me, and they just flipped. See how easy even professionals flip the key. So your hoop is going to have a greater rotational kinetic energy, and it's because of this moment of inertia. Your hoop is just mr squared. Your disk is 1/2 mr squared, so it's been half that. So since your hoop had some of that energy is going to get transferred to more of that hoop's going to get transferred to rotation, that actually means, please erase, that your transitional kinetic energy is going to be less than your disk. So your disk transition is going to be bigger. Remember, this is linear, blue is linear, green is rotational. Because it has the same gravitational, just how does that energy get transferred? Does more of it go to the rotating or more of it go to moving in a linear line? Well, more of it went to the linear line with the disk, so the disk is going to end up landing, going to be able to go further because it has more of a linear velocity when it launches itself off the table. So there you go. Hope that helps. If you have any questions, please ask. Remember, you're loved and appreciated. Bye.